Hi guys, today we're going to move on from the two-dimensional space we talked about previously and move on to three-dimensional space, R3. So, in two dimensions, to graph a point or define a vector, we just needed two numbers. Now in three dimensions, for a point or a vector, we'll just need three numbers. So let's start talking about what it means, how do we think about graphing in three dimensions. Okay, so just like in the 2D case, we're going to have perpendicular axes, one for each of our main coordinate directions. Instead of just x and y, now we have x, y, and z. We want those to be perpendicular or orthogonal. And so since there are a couple of ways you could construct that, the convention that people tend to stick to is what's called the right-hand rule. And so the idea there is that if you point your index finger in the direction of the positive x-axis and your middle finger then perpendicular to that in the direction of the positive y-axis, then unless you've had a run-in with a wood chipper or been the victim of some industrial accident, that your thumb will be pointing in the direction of the positive z-axis. So what you might do right now is take a moment and make sure you see that the coordinate axis I've got right here actually fits in with that, that's obeying the right-hand rule in terms of its orientation. Okay, then once we've got our axes laid out, it's time to start talking about how to graph a point. How do we locate a point in three-dimensional space? So let's talk about the point 2, 3, 5. Well, it's got x component 2 and y component 3 and z component 5. And so if we want to start at the origin, one thing we can do is start from the origin and move 2 units along the positive x-axis, and then march 3 units in the direction of the positive y-axis, and then finally 5 units then in the direction of the positive z-axis. And that gets us to the point 2, 3, 5. Of course, there are other ways we could have gotten there. We could just as well have first, starting at the origin, marched 5 units in the direction of the positive z-axis, and then 2 along x, and then 3 along y. Any combination that you do that in, provided you march all the correct distances along all the correct, in all the correct directions, gets you to the right spot. So that's how we find the point 2, 3, 5. Well, what about vectors? What about the vector with coordinates 2, 3, 5? How's it related? Just like in 2D, if we want to think about putting a base point at the origin, then it's just the vector with tail at the origin, and its tip is at the point 2, 3, 5. And so we can see here that this is that vector that starts at the origin and ends up at 2, 3, 5. And it's got the correct x, y, and z components, where you see the sort of dotted lines showing that connection to the z-axis. The one on the bottom is sort of showing the shadow of that vector in the xy plane. So we kind of get some sense of the depth there. Okay, great. So that's how we can draw vectors. What about the magnitude of a vector? So how do we determine magnitude in 3 dimensions? There's a problem in problem set 2 that relates to this somewhat, and so what I'd urge you to do maybe is pause for a moment and make sure you can work out how do you find that length? How do you figure out the length of this vector v in 3 dimensions? So take just a minute and think about that, and then it's going to turn up on the problem set this week. Okay, if we can find magnitudes of vectors in 3 dimensions, what about vector addition in 3 dimensions? Well, it works. It's completely analogous to the case in 2D. If we want to think about starting from the origin and marching first along the direction of one vector, and then from that point marching along the direction of the second vector, then from the origin to where we ended up at the end of that process would be the sum of those 2 vectors in exactly the same way. And similarly, scalar multiplication, we're just scaling vectors in 3 dimensions, all of their components by the same factor, either up or down. And so scalar multiplication works exactly like you'd like for it to in 3 dimensions. In 3 dimensions, we also have sort of our standard basis. In 2D, we had I hat and j hat were the 2 unit vectors along x and y, and now we just add k hat as a unit vector in the direction of the positive z-axis. So that also works nicely. Okay, and then what about four-dimensional space? What about R4? Or for that matter, R10 or R20? How do we think about higher dimensions? Well, sort of the maybe almost naive approach is just if I want to talk about a vector in 4 dimensions, then it's just a vector with 4 components. Or if I want to talk about a vector in 10 dimensions, it's a vector with 10 components. But in terms of visualizing that, I think trying to visualize 4D space is a really good way to give yourself a headache. But I would urge you on Canvas, on the resources page we've got there, down at the bottom, the interesting stuff, the first link there is to a series of videos called Dimensions, which is all about sort of, it's a multi-part series all about building up to imagining and trying to visualize in different ways what 4 dimensions looks like. And so if you really want to go down the rabbit hole and see what that stuff's all about, I really urge you to watch those videos. They're really well made. They start off pretty simple. It gets pretty hairy after a little while. It's kind of crazy stuff. But have fun with those, and I'll see you in class.